As stated, I'm Bill Corwin. I'll be talking about the two materials-related subtopics within advanced reactor concepts. Before I get started with the technical details, sort of a word from our sponsor. Why do we care about advanced structural materials and how do they fit in the overall program? It's critical to qualify and develop advanced structural materials for these advanced nuclear reactor systems that we're talking about deploying within DOE, the high temperature and very high temperature gas-cooled reactor systems, sodium fast reactors, salt-cooled reactors. Structural materials they have to be able to perform over the full design lifetimes for things such as pressure boundaries, reactor internals, heat transfer components and such. And so the Advanced Reactor Technologies program has put a series of R&D tasks in place to ensure that these things will perform under the long times and high temperatures under which they are required. Moreover, this fits in with the overall scheme of the DOE roadmap that we've got in place for Office of Nuclear Energy, specifically the activities 2 and 3 are the goals, 2 and 3, to develop improvements in the affordability of new reactors and to develop sustainable nuclear fuel cycles. The Advanced Reactor Technologies Office has an extensive program on development and qualification of structural materials. This includes graphite for core supports. We're not going to be talking about that today. We'll focus instead primarily on the work on high temperature metals, but there's also a lot of work that goes on in the area of ceramic composites. A couple of examples that you can see on the screen of advanced reactor systems are the Advanced Fast Reactor, which is a small modular size reactor, sodium cooled, 30-year core life, 60-year total life. The reactor core coolant, sodium exits the core at about 550 degrees C. It's well matched for things like the supercritical CO2 Brayton cycle, which I'll talk about more with regard to the compact heat exchangers I'll touch on as I move forward. A higher temperature system is the high temperature gas cooled reactor system, an example of which is the AREVA HTR system. Triso-fueled, graphite moderated. This particular variant is about a 750 C outlet temperature system coupled with a steam generator, but other examples for this system are the same temperature or higher and are either looking for a Brayton cycle or even coupled for heat production systems and uses just for the high quality heat that they produce. The two topics I'd like to talk about today, which are not really related to one another, RC2 and 2.1 and 2.3, deal with compact heat exchangers and helium tribology issues in gas-cooled systems. The compact heat exchangers are envisioned for use with some of these high-temperature reactor systems to make them more affordable and efficient. It turns out that the compact heat exchangers use a lot less material and by and large are a lot more efficient, plus have a much smaller footprint than traditional tube and shell type of heat exchangers. Moreover, they're well matched for some of the advanced energy conversion systems such as Brayton cycles. SFRs and FHRs are well matched for looking at these in terms of the supercritical CO2 secondary loop. Turbo machinery for that is much smaller and more efficient than traditional steam equipment. And HTGRs may very well use these compact heat exchangers either for gas to gas, possibly gas to salt systems, either for Brayton cycles that are helium based or even for production heat type of systems. However, it doesn't matter. Right now, there are no rules in the ASME code that would allow the use of these compact heat exchangers in nuclear systems, and that's the crux of what the topic deals with. Second system is helium tribology issues. HTGRs and VHTRs both use helium as primary coolant, and with it contains a variety of low levels of impurities. The helium coolant transfers the heat either to a steam generator or a heat exchanger and then on into further things. Metallic components in the primary system and in some cases even secondary system operate in that helium environment. And the concern here is whether the things such as friction, wear, self-welding in that helium environment are affected adversely by the helium environment. So I'll talk about both those in turn. First of all, let's start talking about compact heat exchangers. As I mentioned already, this high efficiency Brayton cycle using SCO2 is of particular interest in reducing cost and increasing efficiency of the systems. The SFR system, sodium fast reactor, is particularly well matched to that, but it, as an example, introduces some complexities. The low pressure sodium that comes out of the reactor itself, about maximum 300 psi, would be matched with very high pressure supercritical CO2 at about 550 C in a heat exchanger. It would be up to about 3,000 psi. And so the disparity of a very high pressure drop across the heat exchanger in conjunction with a moderately high temperature makes for complicated design considerations. For HTGR and VHTR systems, we've got much higher temperatures. 750 C is about the lowest, and for some of the more advanced systems, it may get up to 800, maybe even as high in the long term as 950 C. Again, would be looking at the compact heat exchangers for gas to gas or perhaps gas to salt applications. But in neither case do we have rules to allow this to be done. Types of examples for these systems, just in case you all may not be familiar with these things. A couple of common examples of the diffusion bonded microchannel heat exchanger you can see in the upper left. This is comprised by a series of thin plates or shims in which there have been chemically etched microchannels. And you can see an example of this where the flow channels flow from right to left or front to back in a perpendicular fashion. It makes an ideal series of flow distribution channels. Very good for high pressure. These things are diffusion bonded. They're very widely used in the non-nuclear industry these days. ASME code does have rules for these for non-nuclear systems, and they make them in sizes up to those of tractor trailers for use in the petrochemical industry. But that doesn't mean that we have rules for nuclear issues. Another option are the diffusion bonded or brazed fin compact heat exchangers, in which a corrugated sheet of metal is placed between two shims and then either brazed or diffusion bonded together. Sort of like from the edge, it looks like a piece of corrugated cardboard, but obviously made of high temperature materials. Much more efficient use of materials and larger flow channels for lower flow resistance. And it's possible even to combine these like you see in the picture at the bottom, where you get the best of both worlds. If you're looking for something where you need to contain a high pressure fluid, such as the SCO2, and a low pressure fluid, such as the sodium, you might be able to arrange them in the type of configuration that's shown. However, it doesn't really matter what types of these things you've got. You've got a lot of complex geometries that you have to deal with and the resulting complex stress states. If you look at the micro or relatively small scale geometries, you've got sharp corners, you've got things that are brazed and welded together. These all result in significant stress concentrations, and at high temperature that means redistribution of stresses and complications with trying to figure out exactly how to deal with these things. If you look at the way that the flow channels have to be combined, it results in a very complex arrangement of flow channels and distribution manifolds. If you then have to realize that you have to combine the internals and these external large complex manifolds, you have a real challenge in making sure that the external and the internal boundary conditions match up, and coming up with the stress analysis and the strain analysis that are required for ASME methods to analyze these things is a real challenge, and we just are not there yet for nuclear systems. So what can be done? What is being done about it? Well, the non-nuclear side, ASME Section 8, Division 1, provides a simplified method for looking at these things, which is based on staid rectangular vessels. It's an approximation. You can see an example of this to the right, but it does not consider thermal stresses or cyclic loading. And it does not adequately address the elevated temperature bending and stress strain redistribution that's caused by creep. For Section 3, the nuclear construction portion of ASME code, it does require consideration of thermal stresses and cyclic loading based on stress classification, which is not available in using the Section 8 methods. Thermal stresses are particularly important for allowable cyclic stress, particularly at elevated temperatures, and has to include interactions of the core and the manifold, as well as thermal gradients within the core, both locally and globally. It requires stress classification at this point to be accomplished by deconstruction of finite element results into primary, secondary, and peak stresses. And you have to figure out some way of doing stress classification at sharp corners, which is incompatible with the current methods that are in Section 3. So we just aren't there right now. So how do we get from where we are to where we need to go? Well, there are some potential solution methods that are available. It's possible perhaps to use substructuring, sort of a smearing approach to get equivalent properties that approximate the detailed representation that's needed, but this is still going to require stress classification. A perhaps more elegant approach would be to use the draft code cases in preparation that use the elastic perfectly plastic approach of pseudo-yield stresses to approximate the stress strain behavior of the material. Does not require stress classification and would allow the modeling of all of the detailed thermal gradients and cyclic loading that are required for these structures. Another alternative, or maybe to incorporate into the other ones, is to do experimental approaches to incorporate the effects of sharp corners in the stress concentrations. To look at what effects that these things have in terms of the stress concentration factors, possibly use experimental approaches equivalent to the creep fatigue for creep fatigue curves analogous to the SMT specimens, which were developed to look at elastic follow-up. These allow a design margin to be put on the SN curve from relatively simple laboratory specimens that approximate the kind of design features that one would see as variable sections in actual vessels. So what are we looking for? We're looking for proposals to develop a structural design methodology that would provide an assessment of elevated temperature failure modes for compact heat exchangers under both sustained and cyclic loading due to pressure and temperature gradients. And the results from this would be used as a technical basis to establish the rules in ASME Section 3, Division 5 for the use of compact heat exchangers in nuclear systems. Mind you, we would feel that input from industry would be very valuable, both from the manufacturing side as well as from the designer or vendor side. So please contact your industrial partners as you are thinking about how to do this. Some of the potential solution pathways I already talked about: substructuring, EPP, design methodology, and experimental approaches. One last note, I would mention that there is a draft report that has been completed and is being finalized for publication. It was written by Jim Nestel of MPR Associates with assistance from Sam Sham. ASME Code Considerations for Compact Heat Exchangers. It's going to be published as an OR&L report and should be available at OSTI by the end of the month. Please get a hold of it. It's got a wonderful set of background information and examples of how to deal with this topic. All right, let me move on. Tribology, high temperature alloys, and helium. We've known for a long time that high temperature strength and environmental compatibility in the alloys for these high temperature gas-cooled reactor systems is critical. And the good news is we've done a lot of work on that and by and large found that creep and fatigue of the ASME approved alloys in helium is relatively unaffected by that helium compared to air. However, we are not at all as sure that the impact of the helium on tribology, particularly things like friction, wear and fretting, self-welding, is that we have an adequate basis for a regulatory position on that. The reason for that is the type of oxide layer that is formed in HCGR helium on this class of alloys. If you look at the Ellingham diagram in the upper right-hand corner, section 3 or quadrant 3, which is where most of the combination of carburization and oxidation potential in typical HCGR helium puts the operation of these alloys, ends up with a self-adherent protective oxide layer, but it's not quite the same as what you get in air. And so when you operate these alloys in a condition like that, you need to understand how they behave in those types of behavioral situations. The metallic components that we're particularly concerned about are those that undergo relative motion in this helium environment. Things such as isolation valves, helium circulators, helium control rods, things that slide and move with respect to one another. The materials that we're most concerned with are the high temperature alloys that will be used in the internals or the primary circuit components. Inside the core, alloy 800H, code-approved alloy, is the most likely candidate for construction material. Outside the core, alloy 617 is a very likely candidate. It's about to be codified in the very near future, will not be used in the core because of its high cobalt content. But there may be other materials, hard-facing alloys, there may be other bits and pieces in the circulators that are of interest as well. The types of mechanisms that we are concerned with are friction wear, quasi-static situations such as thermal expansion, vibrations, translation, self-welding, and the components that we're concerned with, control rod drive mechanisms, fuel handling mechanisms for prismatic designs that would move the graphite blocks around for fuel and block modifications during operation, at least the pieces that are resident in the upper plenum. Pneumatic systems for handling the individual pebbles and pebble fuel type of systems. Valve stems and seats, particularly those that may be hard-faced, and helium circulators. So what are we looking for? We're looking for proposals to develop an improved understanding of the potential for enhanced tribological damage to the alloys 800 and 617 in particular, but others as is appropriate, in simulated HCGR helium under the conditions of interest. Again, we are looking for input from industry as well, so please talk to your buddies in the design and component portions of that industry. We would consider that most valuable. And we would hope that the research would focus on both experimental studies, looking at friction wear, self-welding, and whatnot in helium versus air, identify the conditions under which significant enhancement of deterioration in helium might be the case, and what possible mitigation approaches are there. I wanted to make sure you all had points of contact for these two particular subtopics since they're not necessarily listed. I'm William Corwin and Sam Sham at the Oak Ridge National Lab. We are the federal and technical points of contact for these two topics. So with that, I'll turn it back over to Carl.
So our third topic for the Reactor Concepts area, RC 2.2, is electromechanical pumps. This is particularly applicable to liquid metal reactor systems, liquid metal coolants, sodium in particular, and lead-cooled fast reactors are the ones that this would be used in. In an annular electrical induction electromagnetic pump, the traveling magnetic field down the tube in the stator induces a current in the fluid. As you know, when you've got a conductor in the presence of a moving magnetic field, that'll set up a force, and the directional force makes flow occur into that pipe. Astrid is one of the is a French sodium-cooled fast reactor design. They use a ALIP in their secondary loop. They've done some evaluation of that, but they used the matrix method, not truly a model of how this works. It's not a modeling or a code for looking at how the pressure is built up and how it's related to, especially what we're looking at here are the end effects on these pumps. So the correction factors that they put in when they were doing their calculations didn't exactly match, and that we could do some improvement on that. As I said, the three-dimensional currents generated in the regions when the conducting fluids flow through a varying magnetic field. And so they interact with the magnetic field, producing the pressure drop in the pump. Now, there have been proposed some simple methods that were used in the more empirical methods to calculate the effects of these, looking at the number of poles in and reducing your calculations by some just straight factor. But these are no longer adequate. We're looking for something more precise, which we think can be accomplished through a project such as the ones that you could propose. Some of the effects of this, or the impact of ignoring these results or not adequately looking at these results, the top right graph there shows if you totally ignore it, you can get a force calculation as a straight line, but these end effects, how the magnetic field influences the force developed in the fluid at the either end, would actually be quite a bit different at the ends. Then also the bottom left graph, trying to look at the efficiency of these pumps. That would be quite underestimated if you or overestimated, I'm sorry, if you didn't take end effects into account, so if you ignored this. So just going on, so we want to analyze the impacts of these end effects to know them more accurately, to look at the pump efficiency. We want to give that information to designers so that they can do a better job of designing, and also as we do calculations on the operations of fast reactor systems or any liquid metal cooled reactor system, the operations estimates would be more accurate if we have more information about how these end effects work and how we could accurately account for those. We think you could come up with some analyses that could help do this, could even be transformed into modern computational fluid dynamics calculations as well, with some modeling techniques used there. At this point, ask Bill to join me, and we'll take any questions that come up.
The first set of questions are addressed to Bill. Are alternate manufacturing methods for making microchannel heat exchangers also relevant to RC 2.1?
The thrust of the proposed work is to provide a basis for developing ASME code rules. I think that the principal goal is not innovative ways to manufacture compact heat exchangers, but from looking at the methods that are widely used and relatively mature, to understand how to do the required stress analyses and develop the rules, the bases for the rules for ASME Section 3. Not to say we wouldn't consider that, but it's certainly not the primary driver for the compact heat exchanger subtopic.
I'll just make a quick comment on that I did intend to make at the beginning. Yesterday, Tom Sawinski presented the RC1 proposal, which is our mission supporting reactor concepts area, and real game changers, innovative aspects could be proposed for that I think are not are more broadly considered rather than the specific areas that Bill and I covered today, on definitely on materials, definitely on the electromechanical pumps.
Would non-destructive inspection or condition monitoring of compact heat exchangers be of interest in RC 2.1?
Absolutely. One of the bases for concern in developing code rules is how would compact heat exchangers be monitored and evaluated both pre-service and in service, because the current rules cannot be followed for the geometries that are inherent in compact heat exchangers. So yes, that's something that would be of high interest.
Are new test techniques or equipment for testing in RC 2.3 also relevant?
So long as they illustrate the effects of helium tribology on the types of materials in the environments of interest, yes.
So to clarify, development of new structural materials with better performance than the existing alloys are not of major interest in RC 2.1 or 2.3.
Those are both well beyond the scope of those particular work scopes, and they are fairly closely targeted, so no.